Unit 7 is all about sequences and series, and we start off with in Lesson 1 looking at the basics of sequences. Do we remember anything from Algebra 1? Hopefully the answer is yes, but in this quick lesson here, we'll review the things that we're supposed to know from Algebra 1. Consider the sequence b sub n below. We say that b sub n, and what it means is it represents the nth term in this sequence. So this sequence goes 4, -1, -6, and -11. Describe the pattern of this sequence. Hopefully you can look at that and notice that clearly it's decreasing. What is it decreasing by each time? It looks like we're subtracting 5. So the pattern is start at 4. The first term is 4. So the first term is 4. Start at 4. And subtract 5, or add -5, to get to the next term. We keep subtracting 5 to get to the next term in this sequence. Because we have that constant number that we keep adding, that number that we keep subtracting, this is an arithmetic sequence. This is an arithmetic sequence with a common difference of -5, because we keep adding -5, or we keep subtracting 5 to get to the next term. Find b sub 3. b sub 3 means the third term. What is the third term in this sequence? -6. Find the fifth term. b sub 5 means what's the fifth term? 4, -1, -6, -4. Well, the next one's going to be -16. So I subtracted 5 to get -16 there. What's the second term minus the first term? Second term minus the first term. 1 minus -4 is -5. What is the fifth term? Well, we just figured that out. Minus the fourth term. The fourth term is -11. This means the fourth term. So -16 plus 11 gives me -5. Why did both of these expressions here give me -5? Both of those expressions there are representing the common difference. Remember, the common difference is you subtract two consecutive terms. You do the nth term minus the one before it. The nth term minus the one before it. So b sub 2 minus b sub 1 is -5. b sub 5 minus b sub 4 is -5. Because this is an arithmetic sequence where we have that common difference where we keep adding on -5. So if the next question asked you what's b sub 100 minus b sub 99, we don't even need to think, because the common difference, what's the difference between two consecutive terms? It's -5, because we keep adding on -5 to get to that next term. Number 2, sequences don't always have to have an additive or multiplicative pattern. Remember, if they're additive, they're arithmetic sequences. If they have an additive pattern, they're arithmetic. And if they're multiplicative, they're called geometric sequences. We look at those two in the next 2 lessons. We look at those in more depth in the next 2 lessons. But just some vocabulary that your Algebra 1 teacher was supposed to say to you. Consider the sequence a sub n shown below. So we have a sequence here. 2, 4, 6, 8, 0, 2, 4, 6, 8, 0, 2, 4, and it goes on and on and on. Find the following. This means find the fifth term. Well, that's easy. 1, 2, 3, 4, 5. The fifth term is 0. Find the 13th term. 2, 3, 1, 2, 3, 4, fifth term. 1, 2, 3, 4, 10th term. 11, 12. Well, what's going to be next in the pattern? 6. So the 6 is the 13th term. The 13th term in the sequence is 6. So what's a sub 2017? What's the 217th term in this sequence? And this is where we have to think for a little bit, because we don't have a formula to plug into. We have this pattern to follow. Well, the 5th term was 0. The 10th term was 0. The 15th term is 0, so every 5 terms I end up at a 0. So a sub 2015 is 0, which makes a sub 2016, what always comes after 0? 2. So a sub 2017, the next term, is 4. So the 2017th term of the sequence is 4, because every 5 it repeats. Every multiple of 5 was 0. So a sub 2015 must have been 0. And I continued the pattern from there. Number 3, the sequence of squares shown below follows in this pattern until there are no squares left. Okay, so yes, we can count the boxes here, but let's visually see what's happening. So I start off with 16 squares. I lost those 2. I can't even see that. I can't even see that. We started off with a little purple, maybe 16 squares. That's not purple, that's blue, but that's okay. Then we went to 14 squares because I lost those 2. Then I lost 2 more, so I went to 12. I lost 2 more, so I went to 10. So clearly this looks like an arithmetic sequence because I keep on adding -2, or I keep subtracting 2 from the sequence. Our friend Rosie says that this formula here is an explicit definition for this sequence, because she said there's 16 squares initially and each one has 2 less. Does this representation here, does this equation represent this pattern? Well, here's how we check it out. To ever see if an explicit equation represents the pattern, just plug in a number. What's a sub 1? 16 minus 2 is 14. Is the first term 14? No. So guess what? We can stop there, but let's see how wrong a sub 4 is. 16 minus 2 times 4. 16 minus 2 times 4 gives us 16 minus 8, which is 8. Does the fourth term have 8? No. This sequence is not, that formula there is not a correct representation for this. So that's what we figure out tomorrow, is how do we represent these sequences using formulas.